Okay, so today's lecture will be on the time domain behavior from the pole zero clock. Is it clear? Now, till date, everything is clear about the poles and zeros. These are the complex frequency where the system will become either infinite or zero. Okay. Now, I will first of all give you that how the poles will affect the time domain behavior. Now, what happens if any function, okay, let's say fs, will be of which form? I am giving you a generalized form. There will be certain constant h or k, whatever you call, and there will be what? There will be number of poles s minus z1, s minus z2, s minus z3, let's say s minus zn. Right? There are n zeros are there. Okay. Similarly, there will be poles s minus p1, s minus P2, S minus P3 up to S minus Pm. Let there n zeros and m poles. Is it clear? This will be the form of the function, any function. Okay. Now what you will do in order to find out the time domain behavior conventional method? Just partially fractionalize it. Okay. So what will you have when you partially fractionalize it? You have the first term s minus p1 with some residues, let's say it will be k1. Then you have another term with residues k2 associated with s minus p2. You have another term k3 associated with pole s is equal to p3. Like this it is up to 1 k m upon s minus pm. Do you agree or not? Yes. So what conclusion you are drawing from this last expression? That now what you take? You take the inverse of this. You take the inverse of it to find out the time domain behavior. Okay. So when you take the inverse of it, what you find? Each quantity is being described by the so-called pole. Okay. What will be the response of this? K1 multiplied by e raised to the power minus p1 p. Similarly here k2 e raised to the power minus p2. It means, and what is s is equal to p1, what is s is equal to p2, and what is s is equal to p3? These are the poles. Hence the time domain behavior of the system is very much affected by the poles of the system. This to keep in mind. Okay, that zero plays a role in deciding the coefficients, residues. But what will be the nature of the time domain behavior? That is being decided by the poles. So I will give you a generalized picture, okay, that how poles affect the time domain behavior. Generalized picture means we have an S-plane. Okay, S-plane, what are its axes? Imaginary axis and real axis. This is minus 2 and this is minus 0. Now I will take the different location of the poles, and by just looking to their location, I will give you what will be the response of the system. Okay, now poles can be at different location. It can be on the origin. It can be on the real axis. It can be on the. It can be in the form of complex quantity. So by just, or it can be on the same thing. It can be on the right hand half of the S-plane. Poles can be on the left hand half of the S-plane, and pole can be on the right hand half of the S-plane. But for the stability of the system, the pole should lie on the left hand half of the S-plane. And this is what the important term which you will read in your third year control system also. In order the system should be stable. The pole should lie on the left hand half of the S plane. If any pole is lying in the right hand half of the S plane, the system is unstable. And any product or any system will get commercialized or will be in the market only if it is stable. If you purchase a bike, okay, and on the very first kick, if it starts oscillating, okay, then after second year or first year it became stable. Will you purchase this? No, you will not purchase it because at the very initial time it is in unstable form. Okay, so the stability is the topmost criteria for any system or product. Is it clear? And we can judge the stability mathematically by the so-called poles. The poles are lying on the left hand of the S plane. The system is stable. Now let's take some examples. First of all, my pole is lying on the origin. Let a pole is lying on the origin. So origin means what will be the form of system? Something K upon S. K upon S. So what will be the time response? What is the inverse Laplace transform of K upon S? K upon S. What will be the time response? K. Simply K. So time response will be this. So what happens? You make a table. On one side, you make this pole zero plot, and on other side, you just draw the time moment ratio. Make a table. On one side, you draw the pole's location, write down pole location, and other side, time response. Okay, the first diagram will be pole is lying at the origin. So what will happen? What will be the response? A constant amplitude, a step type like response. Is it not? Now let's move to the second point. Let my pole is lying on the real axis. Let my pole is lying on the real axis. Let's say here. Now remove this. So my pole is lying on the real negative axis. Real negative axis. So just think mathematically. Pole lying on the real axis. What will be the mathematical expression of Fs? K upon S plus sigma. Is it not? And when you take its inverse Laplace transform, how it will look like? K e raised to the minus sigma t means exponentially decreasing. Exponentially decreasing. So what will be the response of this? If I plot, I'm drawing plot here. What will be the response? Exponentially decreasing. It's like this. Do you agree? Do you agree or not?
Yes, sir.
Okay, so now take another case. Suppose my pole is lying on the real axis but on the positive real axis. My pole is lying here. Again, what will be the response? First of all, what will be the transfer function Fs? K upon S minus sigma. So when I take inverse of it, what I will get? K e raised to the power sigma t. So what? Exponentially increasing. Exponentially increasing. So what type of response you expect? Do you agree or not? Next, suppose my poles are lying on the imaginary axis. Poles are lying on the, we have considered the real axis, now consider the imaginary axis. And one thing I have told you, what I have told you, if poles are lying on the imaginary axis, then they should always exist in conjugate form. This I have already told you. So let's say this. And these are also simple poles, not multiples. For multiple poles, system will be unstable. Is it clear? So, what will be the form? How much you accept? What will be the form of that expression, function fs? It will be something k upon s square plus 4, x square plus something omega square. Okay, and this term come in which form? Either in sine or cosine. Do you agree or not? 1 upon x. If it is s upon x square plus omega square, then it will be cosine. And if it is something constant upon s square plus omega square, then it is sine. Do you agree or not? Means if poles are lying on the imaginary axis, you will have an oscillatory sinusoidal response. You got my point or not? Yes. So what will be the response? Like this. Do you agree? Of constant amplitude and frequency. Do you agree? Everybody agrees or not? Okay. Now, come. We have taken pole on the origin. We have taken pole on the positive real axis. We have taken pole on the negative real axis. We have taken pole on the imaginary axis. Now take the poles existing in complex conjugate form. First of all, complex conjugate on the left hand arm and then on the right hand side. So, if first of all, suppose my poles are lying on the left hand arm in which form? Complex conjugate form. Is it clear? So, what do you expect? What will be the form? Okay, definitely it will be two terms will be there. One, when I say complex conjugate, so my poles will be 1, 2 will be how much form? Minus sigma plus minus j. Do you agree or not? Okay. Now see, real axis and imaginary term both are existing. Is it not? This real axis will contribute in being a negative term. It will contribute in exponentially decreasing the function. Why? This imaginary term will produce the oscillation. And when you superimpose both, what you will get? And decaying oscillatory response. Mind it? The real term will contribute to exponentially decreasing. While the imaginary axis will make the system oscillatory. And when since both are existing simultaneously, so both net will contribute what? An exponentially decreasing oscillatory response. So I will give you the diagram how it will look like. Now, previously the term called when they are lying on the imaginary axis, it was an oscillation of constant amplitude and frequency. But here the oscillation are different. Here also it is oscillation, but what type of it will be? Let's go to this. What you are getting? Oscillations are there, is it not? Oscillations are there, but what happens to the oscillation?
Exponential decrease.
If you join that peak to peak value, what do you find? They are decreasing exponentially. Are you getting my point? So, if complex conjugate poles are there, lying on the left hand of the S plane, we have an exponentially decreasing response. Now, it's opposite case. If you have a complex conjugate poles lying on the right hand of the S plane, just opposite of it, what will be there? Exponentially increasing oscillations. How it will look like? Like this. If I will join it, the peak to peak, it will be exponentially increasing. So what? This is all about the location of the poles. We have taken all the permutation and combination. what conclusion we are drawing? What conclusion we are drawing? That the location of the poles plays an important role in determining the time behavior of the system. The system time response is very much dependent upon the poles of the systems where they are being located. And also we have got that ultimately our response should reach to some steady state values. And what you find that if poles are lying on the left half of the S-plane, the system will reach to some steady state value. But if the poles are lying on the right hand of the S-plane, it will go on increasing unboundedly. You are getting my point? That is why I have, very at the beginning I have given you a statement that for system to be stable, the pole should lie on the left hand side. Yes. And this is a very important, you can term it as a theorem for all type of systems. Okay, so what, in fact, in control system when you learn in third year, what you will get, that you will have a system, you will mathematically model it. Okay, what we do in our all these academics, that we have a system, we mathematically model it by expressing either in algebraic form or differential equation form. Okay, and then we will analyze this mathematical equation. And how we analyze? By the help of the so-called poles and zeros. So the important conclusion we have obtained from this time domain behavior, the poles are the important parameters of any system which contributes in determining the time domain behavior of the system. This is clear. Sometimes in university exam, 5 marks or 10 marks explain how the poles reflect the time domain behavior. So like this, by drawing this diagram, you can say that how the response is affected. This is clear or not? Yes, sir. Okay. The next topic came here where we have to find out the graphical method for determination of residue. Now this is a very important topic, and every year in the university exam, a question is being asked regarding this. Graphical method for determination of residue. What is residue? First of all,
the remaining.
Oh, that is the English meaning. What is remaining? But in mathematics, you have partial fraction. Okay, with each partial fraction, there is a coefficient is attached. That coefficient is called. Okay, so till date, how we are determining the residue of a partial fraction, of any fraction? Just by substituting that value, okay, in the whole expression, except that expression. Okay, for example, if you are giving like this, suppose the function is there, 5s plus 1 upon s plus 2 into s plus 3, like this. So if I ask you to partially fractionalize, what you will do? You will say there are two poles are there, s plus 2 and s plus 3. Now the coefficient attached to the s plus 2 is called its residue, while some one residue will be associated with s plus 3. How you determine the residue of s plus 2? By substituting s is equal to minus 2 in this expression at all terms except s is equal to 2. Except s plus 2. Do you agree or not? Okay, so when you substitute, what you get? 5 multiplied by minus 2 plus 1 upon minus 2 plus 3. So it will get 5 into minus 1 and 2 minus 1, that will get minus 5. So the residue associated with s plus 2 is how much? Do you agree? Similarly, what you do? S plus 3, substitute s is equal to minus 3 in all terms except that s is equal to s plus 3. So what you will get? Residue 5 into minus 3 plus 1 into minus 3 plus 2. So what you will get? 5 into minus 2 upon minus 1. So you will get 10. So So the residue associated with this 10. Clear or not? This was a conventional method, but now what I have given the heading? Graphical method. What graph till you have in your head? Pole zero plot. What do you have? Pole zero plot. That is on the graph you have. So from pole zero plot, we will find out the residues of these partial fraction. Okay. What is the theory behind it? Let us take the theory first of all. Now, at the very beginning of this class, I have given you the expression of fs. What was that? S minus Z1, S minus Z2, S minus Z3 up to S minus Zn upon S minus P1, S minus P2, S minus P3, then S minus Pn. Do you agree? Okay. So when I will partially fractionalize it, what I will get? Something K1 upon S minus P1 plus K2 upon S minus P2 plus K3 upon S minus P3 plus then upon Kn upon, also it was said that M. So S minus Pn. Do you agree? Do you agree or not? Now, in determining the residue, what you have done, I am again repeating in a generalized form because this will be useful in understanding how from the graph we calculate this K1, K2 and K3. So what you do conventionally, you substitute S is equal to P1 ahead. Yes. So when I substitute, what I will get? Speak out. K1 is equal to how much? H. P1 minus Z1. P1 minus Z2. P1 minus Z3. Dash up to P1 minus Zm. Am I correct? Upon, that is divided by P1 minus P2, P1 minus P3, dash up to P1 minus Pn. Clear? Now comes the important part. We have to understand what these are representing. These are representing nothing but the phasors. What they are representing? Phasors drawn from, what is this representing? This is representing in fact a phasor drawn from the 0 Z1 up to P1. You got my point or not? Is it? Similarly, what is this representing? This is representing in fact a phasor drawn from 0 Z2 up to P1. What is representing? Phasor drawn from 0 Z3 up to phasor drawn from pole P2 up to P1. Phasor drawn from pole P2 up to P1. That phasor drawn from Pn up to P1. And X is the constant association. Clear? So what we are getting? That the residue at any pole is nothing but scale factor multiplied by the phasor drawn from all the product of the phasors drawn from all the zeros up to that pole. What is this represent? Phasor means what? Two quantities associated with phasor: magnitude and phase. Magnitude and phase. So when I am saying phasor, it means mathematically I am what is writing their magnitude and phase. So now just infer from what this whole expression is saying. This is saying that the residue K1 is nothing but equal to H multiplied by the product of the phasors of all the zeros drawn up to that pole divided by the product of all the phasors of poles drawn up to that pole in concern. Are you getting my point? Yes. Similarly, if I ask about the K2, how do you find K2? K2 will be equal to nothing but H scale factor multiplied by the product of all the phasors of all the zeros drawn up to that P2 divided by the product of the phasors of all the poles drawn up to P2. In this way, you have to evaluate it and set that these are the residues, and therefore this is the expression. Take its inverse Laplace transform and you will get the time domain. Just you have to first of all partially fractionalize, but only important thing is that now you have to evaluate the so-called the residues with the help of graphical approach. That is pole zero plot. You got my point or not? Okay, so a question is being asked very in a tricky way. I will give you that statement, that is the transfer function or the impedance function of a, or the transfer function of a given system is this. The current function of a given system is this. Is given to you. Determine its poles and zeros. Determine its poles and zeros. Draw its pole zero plot and hence or otherwise determine its time response. See the statement what I said. What I said, first of all, determine poles and zeros, draw its pole zero plot, hence or otherwise determine the time response of the current. Now what does the statement means? Now you have been given IS. Is it clear? So definitely by looking towards that IS you can find out poles and zeros. Then you can plot also. But the later statement, what was that statement? Hence or otherwise. What does this mean? This means you find out by plotting the plot, either find out from the pole and zero. If it is not possible, otherwise, hence or otherwise. If it is not possible, then first of all say that yes, it is not possible, justify it, and then proceed to some another method. What happens that student in such type of question, they just infer that it means that I can adopt any method. IS is given, okay, I will simply take it inverse Laplace and I will get the IT. But word has technically what has been used? Hence or otherwise, which means that first of all draw the pole zero diagram. If it is possible to find out the response from pole zero, then first of all find out the pole zero from the pole zero plot. If not possible, then you can adopt the second method. You see the technical meaning of the statement. Not that you just infer from whatever method I can use. No. You have the question, the statement clearly signifies that you have to plot through poles, you have to find out response through pole zero. Is it clear or not? Should we move further? Okay. So from now onwards, we will be dealing with the numericals where we have to find out the time domain response from the so-called pole zero diagram. So I will first of all take a very simple example. This is clear? Now one important point in this about the so-called the phasors. What I have shown, what is P minus Z1? It is a phasor which is drawn from Z1 up to P1. So I have to take magnitude. Magnitude means the length of that phasor and its phase means what is the angle. So I am giving you just what does this mean. Okay, because generally mistake is being committed in this only. Suppose this is my pole and there are other zeros and let's say another pole is there. This pole is of my concern. That is my P1 is this one. This is the another pole P2. This is a P1, this is P2 and this is a Now first of all I have to calculate the phasor P1 minus Z1. What does this mean? That I have to draw a phasor from here, starting from here and moving towards this. Arrow will be like this. Okay, so the length of this phasor will be its magnitude. Length of this phasor will be its magnitude of P1 minus Z1. And what will be the angle? The angle will be drawn by taking the reference as this zero, not this pole of concern. Okay, so it is drawing some angle. What is the in mathematics? How do you define angle? Positive angle. The angle drawn from the positive x-axis in anti-clockwise direction. Is it clear? So the same concept will be utilized. You draw one Cartesian coordinate system just in your mind. Not show it, otherwise it will become a very bad diagram. Okay, just in your mind draw Cartesian coordinate system. Now in this case, it is drawing in the clockwise direction. So whatever angle it is there, by applying some trigonometric rules, you find out that angle and put a negative sign over it. So this is the angle. You got the phasor length also, and you got magnitude also, and you got the angle also. Now let us understand better. Okay, this is another pole. You have to find out the magnitude as well as. So starting from here, this will be my phasor length. The magnitude or the length of this phasor will be its magnitude. Do you agree? And what will be the angle? For example, in this case, draw a reference line like this. Is it clear? How much angle this pole is making? Just what is this angle? 0 degree. So this will be, suppose length is 5. So 5 angle 0. You got my point of no. For example, in this case, suppose the 0 was straight forward line here. What will be the angle? Minus 90 degree. Not plus 90 degrees. This is clear or not? So now this you have to keep in mind. So let us take an example. Current IS is given as 2s upon s plus 1 into s plus 2. Okay? Determine IT using pole 0 diagram. So first of all, take a graph paper, draw 2 lines, vertical and horizontal at the center. Now draw its pole 0. How many poles are there? 2. Existing at x is equal to minus 1 and s is equal to minus 2. I am drawing here s is equal to minus 1 and then s is equal to minus 2. How many zeros? 1 existing at origin. Clear? Okay, now when I will partially fractionalize it, what will get? IS will be equal to something k1 upon s plus 1 plus k2 upon s plus 2. Now I have to determine this k1 and k2 using pole 0 diagram. Is it clear? So I will determine, okay, first of all take s plus 1. S plus 1 is I am taking this pole. Okay, what is that formula? 2. So k1 will be equal to 2 multiply by the magnitude and phase of the 0 drawn towards the concerning pole. So this is my 0 and this is pole of my concern. Okay, so I will draw a phasor from here. Is it not? What is length of this? 1. Magnitude is how much? Magnitude is always positive. 1. So 1 will be there and what is the angle?
180.
How much? 180 degrees. It is how much? 180. Sure? Okay, so it is angle 180 degrees. Is the angle zero? No. Divided by. Now one pole is left. This is the pole. Okay. The phasor will be drawn from here to here. What is the length of this?
1.
Okay, so magnitude is 1. And now draw cartesian. What is the angle? Very good. So to this all the solve this, magnitude comes out to be 2, angle comes out to be 180 degree minus 0. You know the phasor algebra of magnitude as well as angle. So 180 degree minus 0 is how much? How much it will be? Just open it. Open it. Do you know how to open up? Oh, T angle theta is given in polar coordinates. This is polar form. Which form is this? Polar form. What will be Cartesian form? E cos theta plus J C sin. Do you agree or not? So what will be B? 2 cos of 180 degrees how much? Minus 1 multiplied by 2 it will be minus 2 and this will be 0. So your residue is how much? Minus 2. So your residue became minus 2 upon S plus 1. Do you agree?
Yes, sir.
Next take the K2. What will be K2? Check it. K2 means now this become a pole of concern. Is it clear? So first of all, what will be scale factor is how much? 2 multiply by how much? How much? Length? 2. Okay, fine. 2. Angle? 180. Angle? 180. Sure? Yes, sir. Okay, fine. No other 0. So divided by now this pole. So draw a phasor from this pole to this pole. How much length?
1, sir.
1. How much angle?
180.
How much angle? 180. Sure?
Yes, sir.
Okay, fine. Good. So if you solve 180 degree minus 180 degree, 0. 2 multiplied by 2 divided by 2 how much? 4. So residue comes out to be 4 plus 4 upon S plus 2. Am I correct?
Yes, sir.
Now take its inverse Laplace transform. What you will get? IT is equal to nothing but minus 2 e raised to power minus t plus 4 e raised to power minus 2t. It is clear or not? So through this example I have demonstrated that how we can utilize the pole zero plot in determining the residues of a given system, and further we can find out the time
response.
Is it clear?
Yes.
So I am stopping here today. Okay, tomorrow we will take some more numericals, okay, related to